Afternoon, everyone. My name is Mohammed, and today I will be discussing my research into the analysis of the cause and effects of part defects in ABS samples made using additive manufacturing. I am a PhD student at the University of West Indies, St. Augustine, and I am a student of Professor Chowdhury. In this presentation, I will go over some background into the research, and I will discuss the methodology that was used and cover what results was achieved, and I will make some comments on those results. And then I would make some closing remarks as well as lay the steps for the future work. Now, additive manufacturing is a broad term that encompasses many different techniques and technologies, but all are based on creating a part by forming layers, one on top of the other. So this research focused mainly on the material extrusion technique. It's known by many different names. The two most common are FDM, fused deposition modeling, but that is a proprietary term used by the company Stratasys for their machines. More commonly in the hobby space, it's known as fused filament fabrication, and that could apply to many different brands of 3D printer using this process. This is a close-up of a single layer. From this, we could see the typical structure with many of these parameters being able to be specified by the user: raster angle, raster to raster, airgap, infill rasters. Now, a raster, each one of these yellow lines, this is the material that was laid down by the nozzle. And we call one of that a raster. That's the tool part that it would take. Now, some areas of interest are what I would call the interface regions. So we have the contour interface region. So we have the contour surrounding the interior of the part, and the interface would be where multiple contours touch each other. We have the contour raster interface region, where the internal raster connects with the contour. And of course, we have the raster to raster interface region. Now, from this diagram, we could also see that there are voids. These spaces are voids where the material is unable to fill. Now, this is just a 2D representation of one layer, but you can imagine multiple layers being built up, that these little gaps become three-dimensional voids or bubbles within the part. Now, some of the advantages of additive manufacturing: you can have high customization. So because it doesn't depend on custom tooling or fixtures to make a part, you can create complex geometry very quickly. This makes it very suitable for high customization runs. Right? Some of the challenges, though, are that even though you have the ability to make very complex geometry, the process compared to mass manufacturing is very slow and very expensive. Also, the strength of these 3D printed parts are usually much, much lower than that of, say, the injection molded counterpart. Okay, and sorry, I've seen something pop up here. Okay, right, sorry about that. Yeah, so the build parameters that I discussed here. So this is just some of the build parameters, and there are actually numerous interactions going on between the build parameters. So it's not easy to predict the performance of your part by selecting certain build parameters or adjusting the levels of certain build parameters because of those interactions. Right? So In the literature, the main focus was primarily revolves around optimizing the mechanical properties of the parts, for example, tensile and compressive strengths. In this research, compressive strength compression was chosen to be investigated. So in addition to the build parameters that we saw just now, I would also look at annealing the parts as a post-processing step to improve the strength or to change the performance of the part. Okay, so this is just an illustration of the methodology that I followed. So in the first step, the part was modeled. So I used SolidWorks to model the part. Now this was based on this design was based on past research where multiple papers looked at compressive strength, the size and compressive strength. Once we have this model, the file is then exported and saved as an STL file, which is a portable 3D model format, and then exported to the slicing software or the CAM software for the 3D printer. In there, the build parameters are adjusted according to the design of experiments. The build files are then exported and printed on the 3D printer and then packaged and stored in an airtight container with desiccant to avoid any moisture being absorbed into the plastic. So once all the experiments were completed, once all the experiments were built, I then went on to test on a universal testing machine. And the failed parts were then observed under an optical microscope where we were able to classify the type of defects and the type of failures that we found in those parts. Okay. Now the samples were built using Arrays 3D N2+. Now the advantage of this particular machine is that it has an enclosed build chamber, which means that regardless of the outside conditions or the ambient conditions, we're able to maintain a consistent build environment. We had thermometers and humidity indicators in the build chamber to make sure that each sample had comparable climate while they were being built, right? So, and also to minimize the effect of ambient conditions affecting the build process. Everything was built on the same day, right? And again, it was stored in airtight containers with desiccant, right? So again, and then they were tested on the same day to avoid any fluctuations in temperature affecting the results, okay? So for the design of experiments, an IV optimal design of experiments was followed, since not only would it allow for two categorical factors to be introduced into the design of experiments, but it's also able to accommodate for higher order models, because the interactions between the build parameters make this a very non-linear process, right? So the continuous factors just mean that we could represent them from 0 to 1. So for example, the layer thickness could be a value from 0 to whatever we specify: road width, air gap, number of contours, build orientation. The categorical factors can't be expressed in a meaningful way numerically. So for example, the infill type, you just have to pick from one of the lists. Same for annealing. It's either the part is annealed or it's not annealed.
Sure, you have 1 minute again.
Sure, thanks. Okay, so this is just a overview. So this is this is some layers that of the 3D printed part, and we have the two types of infill that we use. On the left-hand side, this is the experimental setup. So we have the sample within the compression plates. Okay, so from the results, we bring it into MATLAB and we did a Pareto analysis. And the top 3 influences was the annealing, the interaction between the road width and the layer thickness, and the layer thickness. So those were the 3 main factors that influence the strength. Okay, so these are the 5 classifications that we were able to observe. plane deformation, layer delamination, contour infill delamination, raster delamination, and the layers shared clean apart with no observable deformation. Right, so those classifications we have here, these 5 classifications and their causes. Now, from this diagram, each one of these has at least one cause that is related to the fusion between rasters within that interface region.
Asha, please
okay,
wrap up.
sure. This is the last slide. Right. So from the research, we have the delamination being the most common failure mode. Right, so the user could adjust their parameters to suit, and the top 3 influences were the annealing and the road width, and the annealing and the interaction with the road width and layer thickness. Right, so the user could take into interaction with that. And these are just some of the future work. Right, so we, based on the conclusions, we came up with some of the research that could be done. Okay, so we could go more in depth into the annealing. We could look at other loading conditions besides compression, new materials such as recycled materials and composite materials, as well as more quantitative research into that bond strength. Okay, so this is just some of the references that I use, but a more complete list of references is on the full paper. Thank you, everybody, for your time, and I welcome any question that you might have.
Okay, so we have a question here from your colleague. It's with respect to your choice of testing. You chose to test the compressive strength of the component. Is there a particular application that you use that for? Why was it compressive strength as opposed to, say, tensile or bending or any of those other strengths?
Oh, okay. Well, one of the reasons is that this is just the preliminary research, and the compressive strength, the samples are considerably smaller than the tensile and the flexural. The other reason being that during the compression, there are many cases where you use 3D printed parts for, you put 3D printed parts into those compressive states. So like, for example, a simple thing, if you look at the hobbyist field, a lot of their applications revolve around compression. So for example, when you repair, say, chairs or a lot of the car parts, many of their applications are actually under compression. Right, so those were the 2 main reasons.
Good. Here's another question. You mentioned that there were preventive measures used to help maintain the build quality during manufacturing and storage. But do you think the hot Caribbean climate may amplify the micro defects in the parts when it's used over time compared to, say, a seasonal climatic region?
Yes, well, the thing with the plastics is that they can absorb moisture from the atmosphere. And that could change, well, that does change, sorry, the mechanical properties of the part. So a common example is if you look at PLA parts. Now, it affects all parts, but PLA is has the most prominent effect, where you could print a part out of PLA today, leave it out, and by tomorrow it absorbs enough moisture that it's brittle to the point where if you try to cut it with, say, pliers or something, it could shatter almost like glass.
Okay.
So that's why I had to take so much precautions during the building and during the storing.
Okay. Do you think the fibers in composite materials would make much of a difference to?
I would think so, because from the research here, we could see that the strength in the in the part depends on those interface layers. And if you have, say, a composite material, you might have fibers connecting connecting those interface layers, which will affect the strength of the part.
Okay, all right. One of the reasons why we tend to, well, one of the benefits we tend to think of with respect to additive manufacturing is that it has less waste. But how about what percentage of additively components that are made from additive manufacturing turn out to be defective, so that you have to, so is it a high volume or a low percentage? I mean, because then go ahead, sorry.
I'm saying that's a good question, but it is a very difficult question to answer because there is so much, there's so much variety in the amount of things that you could build. So for additive manufacturing, the two main ways for this type of additive manufacturing, the two main ways are if you make a part that is defective and you need to redesign the part, or if there's say a failure in the building process. So like say power goes and your machine doesn't have any backup, then there is so that's the obvious waste.
Mm-hmm.
Then there's the other one that a lot of people don't consider, and that is what you call support material. So because this builds from the base go up, sometimes you might have an overhang in your geometry, and you need to also build under that overhang to support it. Now, when the part is done, you need to take off that support material, and that's usually a form of, well, that is really a form of waste in the process. So the reason I say it's a very difficult question to answer is because it depends on the geometry itself.
Good. All right. Well, thank you for your presentation, and I wish you best of luck with that, because it sounds difficult to try to keep everything at the same level so that you can actually compare things.
Yeah.